MOSFET. I know a little bit fast, but you can always ask me later, right? So the first part is more to give you have a idea on what cryogenic is about. Now we will go to the physics. So we already talked about the possible application, right? And then why we want that. For example, you have a better thermal conductivity at low temperature, but not necessarily. Your chip might have better thermal conductivity. So when you heat up, you can transfer the heat to the backside quickly. Otherwise, your chip heat up will be, you have reliability issue. Right? Actually, you can link many things. Maybe I take this opportunity to talk about that reliability. A chip that works is great, but in the industry, like this iPhone you use for 10 years still working. So Apple, they are successful is due to some reason, not scam, right? Because their product really is reliable. How do you make sure that every component is reliable, right? Particularly for the chips, it has something called hot carrier injection. Do I have this here? Like hot carrier injection. We will talk about this later. When you drive the transistor to very high voltage, the electron gain a lot of energy. You can do many things to damage your transistor. Okay, and so we also have this so-called NBTI negative bias instability. This is HCI. NBTI is negative bias. This is mostly for PMOS. I don't require you to understand it, but I require you to know what I'm talking about. Why this one has temperature? Any idea? Why people call it temperature? This instability means degradation, reliability issue. When you see temperature, what does it mean? It must mean something. That's why people put temperature, right? It means the degradation is related to temperature. You will see more degradation if you operate the chip at higher temperature. Right? So that's another reason. If we can go to cryogenic temperature, this NBTI will be gone. Right? Electromigration, electromigration. Yeah. So yeah, you feel that electron passing through a wire is very normal, right? But do not forget, it's just like the truck driving on the freeway. You let it drive for 1 million times, your freeway is gone, right? You feel that there's no damage, but you keep damaging. So if you have electron passing through a wire in your chip with high current density, eventually you form a void. The electron has enough momentum to knock off the atom to make the displacement. And then the resistance go up, heat up, then it lock off even faster, a self-fulfilling, a positive feedback effect. Then the wire is broken, then your chip is gone. You just need one void, right, to damage a 1 billion transistor chip. Okay, so, well, if at low temperature, I will have a better reliability, right, because I have less heating. Yeah, of course, also lower resistance. We'll talk about that. Subtraction, so I will talk about that. Maybe not waste the time now. And lower noise. Noise is our main topic in this class. Okay, how to calculate the noise. Okay, so this we will all cover that. So the first technical thing I want to talk about is the thermal conductivity of silicon. What's thermal conductivity? Then this is something for electrical engineer, I always get confused. So I always try to map to electrical conductivity. It's the same. High electrical conductivity means I apply a voltage, then I can get a large current. High thermal conductivity means that I apply, okay, I should say again. For high electron conductivity, I apply a voltage difference, 1 volt and 0 volt. I get a lot of current. High thermal conductivity means that I apply a temperature difference, okay? Like you have hot water in your pot, and then outside is the air, room temperature. We are asking how fast the heat can transfer from high temperature to low temperature. Just like the electrical conductivity, how fast the electron can, amount of electron can move from high voltage to opposite, sorry, right? Low voltage to high voltage. Think about positive charge. How fast the current can go from high voltage to low voltage. If I have an insulator, I have bad electrical conductivity, right? So you can never pass any electron through me, even you have a big voltage difference. If I good insulator like the handle of the pot you used to cook, I can hold it for a long time because it's a very good insulator of heat. The heat cannot pass through it to my hand, even it is very hot. Okay, so the only message I want to, these are some concept I want you to remember. Degree. How do you measure the temperature? Yeah, with here, even this old paper they want to use, I don't know. Doesn't matter. Here degree means Kelvin. Okay, we are going to use SI unit, right? No Fahrenheit, no Celsius, so no argument between whether you are from Asia, Britain, or US, right? Kelvin is the only thing we will use. Now you see that at room temperature, it has a fairly low thermal conductivity, but not that bad actually, okay? But if you go to about 77 Kelvin, it increased almost by 10 to 20 times, which is very important, right? Because if your chip dissipates a lot of heat and you cannot take it away, then what does it mean? It means the temperature will go up. Just like a capacitor. You dissipate, you put a lot of electron on one side of the capacitor and they cannot be drained away because the capacitor is insulator, then your voltage will go up. And then, of course, then you're going to damage your chip, right? So it will be good we have a low thermal conductivity. But unfortunately, when you go to even lower temperature, it drops again, the thermal conductivity. So cryogenics is not always great. You need to find a sweet point, okay? Depends on your purpose. Right? For example, we talk about the high performance servant is that we want to get rid of the heat ASAP because they are very hot. Then operating at 30, 50 or 77 Kelvin is probably the best from that perspective. Okay. Also, there are two curves, right? The top curve or these circles are some good silicon, which has a high purity, only have 10 to the power 12 impurity per cm cube. These cross are worse. They have 1,000 times higher impurity, but still low actually for silicon. But you can see that the thermal conductivity dropped a lot. So with defect, you also affect the transport. Of course, we will not study this, but actually this is some very profound physics topic. It's all about phonon. If you have heard about that, physics people, solid state physics will talk about phonon. They quantize the vibration of the lattice. And the reason at different temperature you have different thermal conductivity is because of the possibility of the mode, just like what we learned in EM, if you have learned about microwave. You have different mode. Some mode can exist, some cannot. Some can propagate, some cannot. At different temperature, then you cause how fast you can carry away the heat. Now, I know I threw a lot of terms to you, right? I don't expect you to fully understand or you can write it down in the midterm. That is not my purpose. But I do want you to try to keep learning this new term, become so familiar with that you take it for granted. Okay? But if you have a question, let me know, right? So for example, if I want to study for this slide, in principle, just for exam, in principle, you can forget whatever I've said. Just only what you need to do is to do the calculation I'm going to show you, right? But what I told you is actually a lot of information which will be useful, okay? So take it if you can, okay? Now, so let's just quickly do a comparison of electrical and thermal conductivity because I always get confused, so I also want to make this clear to you. So in the future, you can use it as a cheat sheet for yourself. So for electrical conductivity, we know we have the current density, right, equals to the sigma times E, right? What is J? Is the current density. What is the unit of current density? Right. Say again? Ampere per. Very good. I put meter square for now. Okay.
So you talking about for we get to touch upon super pairs?
No, we won't talk about Cooper pairs because this is not for superconducting in this class. We may mention it, but it's not a part of the exam. Yeah, but won't go to detail. Okay, current density equal to the conductivity, right? Times the electric field. Keep spelling it wrong. What is the unit of electric field? Thank you. Volts per meter, right? So from here, what is the units of conductivity? You just need to do some division, right? Volts ampere per meter square divided by volt per meter, right? Is this okay what I'm writing here? Or you need to do just this guy divided by this guy, right? So that's why I have ampere per meter square divided by volt per meter is equal to times meter per volt, right? Divided by V divided by M is the same as multiply M divided by V, right? So what does this give me? M got cancelled. So then I have an M here. And then what is volt divided by ampere? Ohm, right? It becomes this. So it's very common. People will also say conductivity equal to 1 over rho, right? Which is the resistivity. And the unit of resistivity, yeah, ohm meter or ohm cm, depends on which unit they pick, but they are all ohm times length, 1/2. I mean, this is some basic thing I think we always need to be clear, right, as an electrical engineer. Any questions? Make it as a cheat sheet that is handy for you. What is thermal conductivity? So we can do some analogy that can help us to understand and memorize the equation. It's something like this, phi equal to, and actually, I forgot to say one thing, I'm sorry. What is the electric field in terms of voltage? Do you remember? It's negative dE, what is that? How is related to the potential electric field? It's the gradient of the potential, right? dV dx, negative dV dx. Right? You have 1 volt here, 0 volt here, distance is 1 meter, then electric field is 1 volt per meter. Make sense? Yeah, so here I forgot to mention this. The reason, and that's why you get volt per meter, right? Do you see this? Because your volt divided by distance. That's why you have volt per meter. Now, how about for thermal conductivity or thermal equation? It is negative kappa dT dx. Okay, so you compare these two equations. Let me write it down what it means first. This phi is the so-called heat flux. Right? So we don't have heat molecule. We don't have this, right? But at the old time, people think that there's some carrier for heat, and that is like, I don't know what they call it, just a particle that is for heat, right? And the reason you lose the heat because this heat particle goes away. Just like the electricity, you lose the charge because the charge particle goes away, right? So this heat flux is just like here because you have J. What is J? J is the amount of electron per second passing through an area. Heat flux is like this, is the same. So it is volts per meter square. Just like what you have here. Ampere per meter square is what? The power. How much power go through an area, right? Equals to the thermal conductivity, right? Times dTTx, which is the gradient of the temperature. And what is the units of gradient of temperature based on this equation? dt dx. What's T divided by x? Thank you, K over M. Very similar. This is V over M, and this is K over M. Right? So their conductivity is what? Thermal conductivity. It's just like what we have done. W over M squared times M divided by K, which is equals to 1, but we will just follow the tradition. We will write it as W divided by Km. If I say Km, you will get confused, right? K dot M. It's not kilometer. So maybe you cannot memorize right away, but my message is this. The heat flux is just like the current density. Current density is saying how much current going through an area. Heat flux is like how much heat generated per second going through an area. The temperature is just like the voltage, okay? And then the thermal conductivity is just like the electrical conductivity. Now, why this is so? If I test you, you will have a cheat sheet. I don't ask you to memorize it, right? But the point is that in the future, when people talk about the thermal conductivity, how it dissipates the heat, if you cannot get it, correlate it with the electrical quantity. For example, they say the top of the chip is 100 Kelvin, 400 Kelvin. The bottom is 300 Kelvin. And it dissipates very slow because it has very large thermal conductivity. If you don't understand, just think about that. It's just like the top of the chip is 400 volts, bottom is 300 volts. But the current cannot go through quickly because I have very large electrical resistivity. Think in that way. At the way you used to analyze because you have the same equation, right? The ways you used to analyze the electrical quantity will be similar to the thermal one. Okay? The reason I want to introduce, because when you talk about temperature, if you don't know this equation, it doesn't make sense, right? But again, this era is no longer memorizing, right? You have ChatGPT, everything, but you need to know the concept, how it is related to what you have learned. So what I want you to get is have a feeling on them right away. Try to feel it, right? Feel an instinct instead of like you need to do the equation, right? Okay, any questions? Now, if no, I will just quickly go through this graph. How about for the interconnect? Maybe we did not emphasize too much in other classes. In a semiconductor chip, you have a lot of transistors. But nowadays, more important is the connection. Nowadays, the transistors are so fast. We talk about 2 nanometer, what they call 20 angstrom now, right? 5 nanometer technology. Of course, the transistor is not really that short, but transistors are very fast. So what is limiting the growth, the speed of the transistor, is actually the interconnect. Okay, just like in a city, you want to travel, you have talked about the commute. Commute is difficult. Maybe in the past is that you don't have stairs. You don't have elevator. You always need to walk through the stair. That part actually takes you a lot of time when you go to work. But now you have elevator. You're so fast. And now everything is the road, a lot of congestion, making the communication slow. Now this is the bottleneck in every advanced semiconductor technology. If you can solve this, then you'll be a Nobel Prize winner, right? But we know there is a limitation. But anyway, the point is that and you also know that for metal, when you go to lower temperature, you have higher electrical conductivity or lower resistivity. This plot shows the resistivity. So when you go to lower temperature, it actually will keep going down. Make sense? Some metal, like aluminum, niobium, when you reach 10 Kelvin, 4 Kelvin, or 1 Kelvin, I forgot. Niobium is 10 Kelvin, 9 Kelvin. You become a superconductor, which is great. But some metal, they never become a superconductor. For example, copper. And this is very ironic, right? I hope you have this concept also. A good conductor usually cannot be a superconductor. The reason is because of the BCG theory. What they discovered, why this superconductor is because the lattice, the atom, the nucleus, they interact with the electron. If you have a strong interaction, then this enables the superconductor. And why you have a low resistivity for some metal? Because you don't have interaction, right? So that's why you cannot be a superconductor. Pretty funny. All those high temperature superconductor, they are very bad conductor at room temperature. Okay? But anyway, one message is that copper cannot go to superconductor. Now, actually, this is useful to me, right? I taped out an LNA last year, and I was measuring at different temperature, and then I was suspecting maybe at 4 Kelvin, I get very good performance. And now, after I preparing this slide, I realized that, it reminds me, actually, it's not a superconductor. It might have some residue value, and that's why my 77 Kelvin one might have the similar performance as the 4 Kelvin in terms of the resistance. Okay? Now, so what he's trying to say here is, yes, when you go to lower temperature, the resistivity reduced quite a lot, 10 times, 20 times, but then it will saturate. And that's what people call the residue resistive ratio. If you have a large ratio, it means you saturate at a lower value, right? Not that important for this one. But you just say that for different quality, the reason they have different saturation level is because you have different type of quality. You remember when you go to very low temperature, you don't have the phonon scattering already. Your atoms are not vibrating as much, so your electron can pass through easily, right? Then you thought that you will have a very low resistivity. But unfortunately, now all the impurity, if you don't have a good quality, dominate. Okay? It's just like in this classroom. If you want to run from here to there, and all of you try to vibrate vigorously, you're going to hit me. I cannot run very fast. Very high resistivity. And when I cool down, you guys just sit still. You are not hitting me. I can go very fast. But because of defect, someone put the chair in the middle of the row, right? So in the past, maybe when you're vibrating, you're still hurting me. And when you cool down, they are a little bit faster. But now it's dominated by the chair on the row. And that's why you have this residue. Now, this is pure copper. But in semiconductor, we have very thin copper. It has a lot of boundary. You may have something like this. This is a cross-section of the copper. Actually, they don't use copper now. You have some nylon, right? So they actually may use ruthenium or other metals, right? So you have another layer of, so you are going into the screen. Now, this is the transport. But on this might be the copper, but on the edge, it might be another like titanium nitride or whatever surrounding it. Because it's so small, your electron actually feel them, because electron is a quantum object, it's a wave. Okay? My message is just that the boundary scattering becomes very important. Okay. So I only talk about silicon and copper, right? And that's what I want to talk about material. Now I want